So day by day, with the advent in the technology and the miniaturization process, the size of all the components are reducing, and we have reached to a point where you can have a small insulin pump system built into the human body, which will continuously monitor the blood sugar level and automatically injects the amount of insulin to the patient's body even without the knowledge of the patient. And similarly, you have the heart pacemakers also, the small embedded device which will be built into the human body in order to stimulate the heart beating. Now, embedded domain also, compactness is the significant deciding factor. Now, when I take the embedded domain, it's not necessarily in the embedded domain, even in any other domain you go, miniaturization is the trend now. Now, even with the desktops or the computers, if you take, the size of the computer system is reducing. Now, 1945, when the first modern computer came, it used to occupy an entire room. And with the with the advancement in the technology and the creative innovations, the size of the computer system is reduced, and at the same time the performance is also increased. So you have now the laptops and even the palm tops also. And most of the application demands the small size and lightweight products. That is what they demand. And there is no application which demands the large and heavyweight products, and all the applications these days have a huge demand for the small and the lightweight products. So next is the sixth important characteristics of the embedded system is the power concerns. So power management is another important factor here, because the embedded systems are handheld devices and majority of them are battery operated. And when you're designing the embedded system, you got to design it in such a way that they consume very low power. With this, you can increase the battery life, and you can make the embedded system operate for a longer period of time with minimum charging. Now, embedded system, and when you're designing, so this is what you have to take care. You have to design in such a way that it minimizes the heat dissipation. Now, if an embedded system dissipates too much of heat, then you got to have a cooling requirement. So then you got to fit an extra cooling fan. So if you're not able to put the extra cooling fan, so then it will break down the embedded system, or it will break down the microcontroller after it reaches a certain amount of temperature. Now, for that reason, and again fitting an extra cooling fan will make the embedded system bulkier. Now, we don't want the system to make it bulky by consuming additional space, for adding all this cooling fans and all. Now, what we got to do is, now we got to minimize the heat dissipation itself. If we're able to successfully minimize the heat dissipation itself, then we don't need to have the cooling fans. Nowadays, ultra power, and even one fortunate thing is, nowadays we have ultra low power components. Now, and when you're designing the embedded system, you should go for using the low power components. So when you're using the low power components, obviously the heat dissipation will be reduced, and you don't have to use the cooling fans for cooling the temperature from the components. So low power component, and LPC2148, what we have understood, the microcontroller which we're using all these days is again a low power controller. LPC itself stands for the low power controller, because it operates with only small voltage, that is 3.3 volt, and it is not even taking 5 volts also to operate. Now, why this is a critical constraint in embedded system? Because majority of the embedded systems are battery operated applications. So till now you understood the main important characteristics of the embedded system, 6 characteristics of the embedded system, starting from the application and domain specific, reactive and real time, operates in the harsh environment, distributed in nature. So it's not like an embedded system should be an independent one. An embedded system can be a part of the larger system, and all of those embedded system within the larger system, so they work together in order to achieve a common purpose or a goal. Next, small size and weight, lightweight, power concerns. So these are the 6 important characteristics of an embedded system. So next, what we are going to understand is the quality attributes of the embedded system. And when I say quality, so they are something related to the non-functional requirements of the embedded system. Now the non-functional requirement that need to be documented properly, the quality attributes of the non-functional requirements that need to be documented properly in any embedded system design. And the quality attributes which you consider here, are more concrete and measurable. And again, so as I already told, when I say the quality attributes of the embedded system are the non-functional requirements, they are not directly related to the services offered by the embedded system. Instead, they are related to the behavior or the performance of the embedded system. I gave you the example of bicycle. I can give you one more example. Say 2 ATM systems. The ATMs where you draw the money. Say there are 2 ATM systems, ATM 1 and ATM 2. Both of them provide the same services. So whatever the both ATM system, so they provide the same service. Withdrawal facility they provide, fund transfer facility they provide. So they provide the balance inquiry facility, and they provide you the mini statement facility. These are the services what both of them are providing. Let us assume the ATM 1 is available 24/7. Even midnight, 12 o'clock, if I go there, the ATM is up and running and I can withdraw the money. See, ATM 2 so provides service only 12 hours per day. Same services both the ATMs are providing, but behavior wise they are different. So that this provides service 24/7, but the other one provides only 12 hours service. The behavior wise they are different. So the ATM 1, now the moment I insert the card and enter the amount to withdraw, so it dispenses the cash to me within 30 seconds. So when I go to the ATM 2, say I insert my card and enter the amount to withdraw, it takes 3 minutes to dispense the cash. So this is doing it in 30 seconds and that is doing it in 3 minutes. Ultimately both of them are providing the same service. So that there also the cash is dispensed and here also the cash is dispensed. But the only difference is it did that, the first ATM did that in 30 seconds and the second ATM is doing it in 3 minutes. The performance wise they are differing. But ultimately they are providing the same service. That is what is non-functional requirement. And here, so the quality attributes of the non-functional requirements of the embedded system, and again can be broadly classified into these 2 types. One is operational quality attributes are the non-functional requirements, so that are exhibited by the system when the system is functioning online. And these are the non-functional requirements are the quality attributes that will be exhibited by the system when it is under development or testing. Now this is what I told. I have them side by side just for better understanding. So first we'll understand the operational quality attributes. Represents the relevant quality attributes related to the embedded system when the embedded system is in the operational mode or online mode, when it is providing the service. So these are all the quality attributes which define the behavior of the system when the embedded system is online and providing the service. Now one thing, I can say the example for the operational quality attribute is the response. How quickly the embedded system responds to you. Now I gave you the example of the ATM. So one ATM, the first ATM was dispensing the cash to you in 30 seconds, the other one was taking 3 minutes. That is how both of them were doing the same service, but the response wise they were different. So this was 30 seconds and that was 3 minutes. And then another important operational quality attribute is the throughput, that is measured or that defines the behavior of the system when the system is online or providing the service. That is throughput. What is throughput? Throughput is normally defined as the amount of work done per unit time. How much amount of work you are able to do. Say for example, I have a web server. When I say web server, now the throughput of the web server can be defined by how many web pages it is able to process per minute. So if the web server is able to process too many web pages per minute, then I say its throughput is high. That means it is doing more work in what per minute. And similarly, if I take a database, so if it is able to perform too many transactions, larger number of transactions per minute, then I say its throughput is good. Similarly, if I take a file server, if the server is capable of processing large number of input files, so then I say its throughput is good. The amount of work done per unit time is good. So that is what is throughput. And again, throughput also defines the behavior of the embedded system when it is online and providing the service. Reliability, this is something related to the failure rate. So this also defines the behavior of the system. Now, if the failure rate of the system is very low, then I say it is highly reliable. So for example, the best example, the two ATMs which I was already talking. So the first ATM, so failure, it fails once in a year. And the second ATM, let me assume it fails 10 times a year or 12 times a year. Now which one you call highly reliable? The first ATM is highly reliable because it fails once in 6 months. I'm telling it fails once in a year. Sorry, it fails once in a year. That means it fails once in 12 months. Whereas this second ATM, it fails 12 times in a year. That means every month it will be failing. And the reliability of that system is very low. That means it is an unreliable system. Whereas the first ATM is highly reliable. Why you say it is highly reliable? Because the failure rates are less. Because it fails only once in a year. And this ATM, the second ATM fails, so 12 times per year. And next is maintainability. So this is again another important factor, operational quality attribute of an embedded system or any system in general. So this says how easy it is to maintain the system. Now maintainability is required because when the system is online and functioning, any point of time, so something can happen to the system and it can go down. Now what is maintainability? Now how easily you can fix that? If you're able to fix the error and make the system up and running in less time, then we say it is highly maintainable. Say the system goes down, the first ATM goes down, and if you're able to rectify the fault and make it function within a minute or within 10 minutes, then it is highly maintainable, easy to maintain. If I say the system is down and you require 10 days to function it, so it's not maintainable because you require 10 days to repair it and make the system provide the services to the user. And for all this 10 days, which it is offline, for repairing, will not be providing any service. And that means it is not available for the user to get the service. That is what is maintainability. And security is another important operational quality. These are all the operational quality attributes because the attributes exhibited by the system when it is functioning. Security, how secured it is. When I say security, it should protect the confidentiality. That means it should not disclose the data to the unauthorized users. That is what is confidentiality. And second is, so the one more important thing is after confidentiality, integrity. It should not allow the unauthorized user to damage your data. That is one more important thing. And then one more important thing is it should make the system available at all the time. And safety is the sixth operational quality attribute. Now what is safety? Safety and security, are they same? No. Yeah, so making the system secure will make the system safe. Or this safety what we are discussing here is totally different from the security what we understood. Now security is mainly to protect the data from unauthorized disclosure and unauthorized modification and unauthorized availability. Now safety is more related to the damage that may be caused when the embedded system goes down or when the embedded system breaks down. Say for example, mission critical systems. Now I told air traffic control system or the flight control system. If the embedded system goes wrong there or breaks down or goes down, what will happen? Then there is the damage caused, the airplane and also to the passengers. And if an embedded system which is there inside the industrial plants or the nuclear power plants, if something happens, then again there is a threat caused to the entire physical surrounding. Now safety is more related to this. Now when we come to the other side, non-operational quality attributes, the attributes that are exhibited by that must be executed by the system when it is under development. Now it's written here, so addressed for the product not on the basis of operational aspect are grouped under this category. So these are not the quality attributes which are exhibited by the system when it is under operational mode. These are under the development mode. One is testability and debuggability. How easy? Say I'm developing an embedded system. I've finished developing the embedded system. Now before putting it into use, before putting it into provide the service, I have to test it. Now how easy it is to test my system? We go to test? We go to test in order to ensure whether the system what you have developed is behaving as per your requirement or intended behavior, whether the embedded system is exhibiting the intended behavior or not. In case when you test the embedded system, and if it is not behaving as you expect, then what is that you have to do? You should go for debugging the system just to find the location or the place where you have deviated from the expected behavior. So that is what is testability and debuggability. Now how easy it is to test and how easy it is to debug. And next what we're going to discuss is evolvability. Even the embedded systems, so we'll go for evolution. And same with the case for the human beings also. Now we the human beings, there is a theory that we are evolved from the monkey to what? The man, or the apes to man. And the same thing happens with the embedded systems also. When you design the embedded system, so the same embedded system with the same hardware and firmware technology will not remain for all the years like that. Now even the embedded systems, as and when the technology changes, the hardware used in the embedded system will get upgraded, and even the firmware will also get upgraded. Now when you're designing an embedded system, you have to design it in such a way that it can be easily evolved in future by adding additional, by adopting the new hardware technologies and firmware technologies. And next is the portability. When you're designing an embedded system, you go to design whether it may be an embedded hardware or whether it is an embedded firmware. You go to design and develop it in such a way that it will run on many different hardware and software configuration. Portability, that is surviving anywhere. And this even applies for the normal humans also. Now if I am able to survive any place on the earth, then I call myself as portable person. Correct? Now, time to prototype and market. This is one more thing. Now, when any systems which are developing, it will always starts from the idea or the conceptualization. So first you got to ideate. Now after ideating, then you go to design, and then you got to develop an initial prototype or the basic model. After developing the basic model, you got to expose that to the users. Don't let the user start using it. And when the users start using it, they'll give you the feedback or the comments. Based on that feedback and comments, you improve your concept or the ideation, and then go for developing the actual model, actual product, and then go for marketing it. So these are all the non-operational quality attributes again. And then per unit and total cost. This is also important. Now after you ideate and you develop the prototype for it and expose it to the users, and based on the feedback given by the user, when you go for finally actual implementation, when you do the actual implementation and market the product, so while marketing the product, this will come into picture. Now what is the price per unit? What is the price of the product? Initially, when you're pushing your product into the market, you cannot have a very high price. You got to push your product to the market with a nominal rate. So if initially if you try to push your product to the market with a very high price, then there is you may have to face the marketing risks. Now for initial some days, the rate of the product should be fixed to the nominal rate, and as the time progresses, gradually, so you can go for increasing the cost of the product. Now these are all some of the operational quality attributes and non-operational quality attributes. Now the response, as already told, the quickness of the system, how quickly the system is able to respond back to you. So that is called as the response. Now if the system is able to respond back to you very quickly, then we call it as a very good system and as a very good response time. Now, and majority of the embedded system these days, they demand fast response, and it should be almost real time. Now examples, as already told, in the file controlled application, it must be real time. The response time must be very fast, and the delays are not entertained. Now, and it's not necessary that the response time should be real time in all the embedded system. So only few embedded system which we call them as mission critical system, there the response time must be less or fast. Now for example, where there are certain embedded system where the response time need not be real time. Say for example, many of the embedded system will see electronic toys are also embedded system, and they are not mission critical system, so there the response time can be even less also. Response times can be more, throughput. Now as I already told, throughput is defines the efficiency of the system. Why it defines the efficiency of the system? Because it defines the rate of production. Now how much you can produce per minute, or how much amount of work the system is able to do per minute. That is what is the throughput, and again the throughput of the embedded systems must be good. Now if I take an example, the card reader. Now what is the throughput of the card reader? Now I say the throughput of the card reader is good only when it is able to read too many cards per minute or per second. And throughput is a benchmark. What is a benchmark? Benchmark is something as a standard reference or the standard point by which you can measure or compare something. Now next one is the reliability. As I already told, the system is highly reliable if it has very less failure rates. Now is a measure of how much percentage you can rely upon the proper functioning of the system, or what is the percentage susceptible of the system to failure. Now we have two things with respect to the reliability here: mean time between failure and mean time to repair. And in addition to these two, there is one more thing called as MTTF, mean time to failure. Now what is MTTF, mean time to failure? The time and once in how many hours, usually MTTF, mean time between failures, and mean time to repair, they are expressed in terms of hours. Now when I say MTTF, then once in how many hours the system will fail. That defines, MTTF defines in how many hours, once in how many hours the system is going to fail. Now this mean time between failure is the it gives the frequency of failures in hour, or weeks, or months. How many times a system has failed in 1 hour, how many system have failed in week, how many system have failed in a month. And similarly MTTR specifies how long the system has taken to get repaired after its failure. Now the reliability can be defined with respect to these two things. So mean time between failure should be very less, and mean time to repair should be very less again. So when the system goes out of order, so within no time, if you're able to repair it, then again the system's reliability is more. Now maintainability, as I told already earlier, now it is how quickly you can correct when the system goes out of order. How quickly you can fix the system when it goes out of order. Now, reliability and maintainability are two complementary disciplines here. Now, why? Because if I say the system is highly reliable, then you don't have to maintain it. I gave you the example of two ATMs, one ATM failing once in a year and another ATM failing 12 times a year. Now, the system which fails once in a year, we call it as highly reliable, and maintainability for this system is required only once in a year, whereas the maintainability of the other system which fails 12, which assume it fails 12 times a year, 12 times you got to maintain. That means if I say the system is highly reliable, so the maintainability is reduced, and if I say the system is not highly reliable, then the maintainability increases. And another important thing is the maintainability is closely related to the system availability also. If I say the system requires more maintainability, then the system is not available for the user service. Say for example, I'm using a motorbike and my motorbike requires 12 servicing per year. That means every month I have to leave it for a service. Now, then in a year, in 365 days, the bike is not available for my service in 12 days. On all other dates it is available for my service. If I say as the maintainability increases, what will happen to the system availability? Decreases. They are inversely related. If I say a system requires more maintainability, then the availability will also go down. Now, if it's the same bike example, if I assume the bike requires 12 servicing per year, now the bike is not available because I have to leave it to the garage for 12 days a year.